equals to Q into E. Q cancel. This velocity is coming out to be E by B. Particle is going circular also, but it is moving forward also. Correct? Circular motion plus moving forward. So this way, I am drawing like this. Suppose this is the helix motion. This is my water bottle. If I rotate, if I give one rotation, it will go up now. So if I rotate by one revolution or one rotation, if I give one rotation, how much forward distance it moves? This is called pitch. Equals to Q into E. Q cancel. This velocity is coming out to be E by B. Now this velocity is called velocity selector. Velocity selector. Now what is this velocity selector? Means how we should choose the velocity. How we should choose the velocity so that charged particle moves in the straight line only. Okay, this is called velocity selector. How we got this formula? We got this formula when I told this Fm is equals to QE. Means this magnetic force is equals to what? Electrostatic force. When these two forces are equal, so what will happen? No net force on the charge. If no net force is on the charge, the particle will continue to move in the straight line. Okay. When we arrange this formula, that is Fm equals to Fe, QVB equals to QE, Q cancel. So V is coming out to be E by B. Means if you set the velocity of the charge in the ratio of electric field to the magnetic field, then that velocity, if you project the charge now, the charge will not have a parabolic motion. The charge will continue to move in the straight line. Okay, so write this. This is called the velocity selector. How you should choose the velocity so that the particle is moving in the straight line under the influence of electric field as well as magnetic field. Okay, see. Now, I told one case that if the magnetic field, see, if the magnetic field is perpendicular to the velocity, see this carefully, if this magnetic field is perpendicular to the velocity, so what kind of motion we were getting?
Circular motion.
Everyone, what kind of motion we were getting? Circular motion. If magnetic field is perpendicular to the velocity of the charge, we were getting circular motion. Okay. So the charge will execute circular motion. If the magnetic field and the velocity of the charge are in the same direction, then what will happen?
Straight line.
No force, so the charge will move in the straight line. So here straight line motion, and here we have circular motion. Now if I mix these two cases already you have studied. Okay, you have already written, no need to write, already we have studied. But what I am saying, if I mix these two cases, like suppose magnetic field is in this direction and the charge is moving in this direction. Charge is moving in this direction, making an angle theta with the magnetic field. Correct? You understood? What is happening? Right now, the charge is moving. This is the charge. This is moving in this direction. And this is the direction of magnetic field. So velocity makes an angle theta with the magnetic field. Now what we can do? They will ask like what will happen? What will the motion of the charged particle? Okay. So basically this velocity can I resolve in two components? Velocity can be resolved in two components. So this we can draw, like we can say this is equivalent to velocity two components I will draw. One component like this, one component like this. So what I told in the basics, you rotate the velocity vector across this angle theta, which component? Cos theta. So this will be v cos theta, and this component will be v sin theta. Correct? Clear? So this component is v cos theta, this component is v sin theta. Now what we can see, that v cos theta is in the direction of magnetic field. Correct? V cos theta is parallel to magnetic field. Correct? And v sin theta is perpendicular to magnetic field. Correct? Means due to v sin theta, due to this component, particle will execute what? Circular motion. See here. When the velocity is perpendicular, see here, velocity is perpendicular to magnetic field, particle was executing circular motion. And velocity, when this is parallel to magnetic field, the particle was executing straight line. Now here, this component, due to this component v sin theta, the particle will execute circular motion, and due to v cos theta, the particle will also execute straight line. Now circle plus straight line, what kind of motion you can expect? Circle plus straight line, spiral motion. See this copy. Particle is going circular also, but it is moving forward also. Correct? Circular motion plus moving forward. So this will be the motion. Helix. We call this helix. Correct? Like see. What will happen? Due to, see here carefully, due to v sin theta, particle will execute circular motion. So I am drawing like this. So suppose it is executing circular motion. At the same time, this component will move it forward. So that's why the motion will be like this. Correct? Fine. So circular plus, here we will get circular plus straight line, which we can call helix. Correct? So write it down. Achha, you know pitch? Pitch. Class 9, 10th we used to study pitch. What is the pitch? Cricket pitch. Virat Kohli is batting. Okay, Mitchell Stark is bowling. So that pitch we call pitch. No physics, pitch. See, like I will tell you what is the meaning of pitch. This is my water bottle. If I rotate, if I give one rotation, it will go up, na? So if I rotate by one revolution or one rotation, if I give one rotation, how much forward distance it moved, this is called pitch. Okay, like you can see one rotation, suppose you mark here something and again you rotate like this, one rotation, one complete rotation. So how much it goes up, how much distance it goes up, this is called pitch. Again I rotate one, see again it went up, again I rotate it, again see it is going up, na? So this is called pitch. Forward pitch is basically forward distance moved in one complete rotation. So in this helix motion also, now they will ask what is the pitch. Like see, I am drawing like this. Suppose this is the helix motion. This is how our spiral bindings look like, correct? Executing circular motion as well as moving forward, like spring also, spring. It goes circular, you can see circular motion also, and it is moving forward also, okay? So, this distance will be called pitch. In one rotation, how much forward distance it moved? Pitch. So pitch, how we can calculate the pitch of this helix? Pitch means we are dealing with forward distance, this distance. So pitch, can I write? This distance can we write? Distance equals to speed multiplied by time. What is the speed in this direction? So speed in x direction multiplied by time. What was the speed in this direction? See, v cos theta. The speed in this direction is v cos theta. So we can write v cos theta multiplied by time. In how much time it is going forward? In one complete rotation. In one complete rotation it is moving forward, and this distance we are calling pitch. So time we will take one complete rotation time, na? One complete rotation time. What is the time for one complete rotation? Time period 2 pi m by qb. So time will be 2 pi m by qb. So this will be the value of pitch. They asked in the examination, what will the pitch of the helix? So just you remember like this. Don't remember like this, v cos theta into 2 pi m by qb. This will be a bigger formula. You just remember pitch equals to, pitch is the distance equals to speed into time. Speed is v cos theta and time of revolution 2 pi m by qb. Write this. Okay, fine. Written. So what you can do now, you modify your formula. The time wherever you have written now, like radius of the circle. What was our formula? mv by qb. Now what you do now? You write like this, v perpendicular. There will be no changes. If you write v perpendicular also now, there will be no changes. Let me show you. See, why I am writing v perpendicular? V perpendicular is that component of velocity perpendicular to magnetic field. Like see, here if I write, come to the first slide. See, here R equals to mv by qb. Here automatically this magnetic field was what? Perpendicular to velocity. So that's why I have not treated, because automatically this velocity is perpendicular to velocity. This velocity is perpendicular to magnetic field. So you can write also, you can leave out also. But why I am writing now? Whenever they will give velocity making some angle theta with magnetic field, this will help you. See here. So velocity is making some angle theta with the magnetic field. So it will have two components. One component v cos theta, one component v sin theta. Now if I am asking radius, so in radius the formula is mv by qb. Okay, mv by qb. Now you know that this component is not going to help in executing circular motion. This component will only help for circular motion. And this is what component? Perpendicular component to velocity, to magnetic field. This component is perpendicular to magnetic field. Magnetic field in this direction, and this is 90 degree, correct? So that's why I am making you write v perpendicular, correct? Because you won't get disturbed during the examination. Right now it must be clear that okay, v sin theta is there. Later on you will forget, because if they give like this, see, for example, uh, they have given magnetic field in this direction. Suppose they give velocity in this direction. They give this angle theta, suppose. Correct? Now what will happen now? If you have remembered this formula, R equals to mv by qb, and v perpendicular, suppose you have mugged up that here v perpendicular was v sine theta. So you will write, if I ask what will the radius of the circle, so you will write, sir, radius equals to m v sine theta by qb. The problem is actually they have changed theta from here to here. If this is theta, can I write this component? See, take v vector and rotate it towards theta. So this component will be what? V cos theta. And this component will be what? V sin theta. Now what I told, if you are writing radius, so you have to take mv perpendicular component. So now my radius will be mass perpendicular component. Now this component is perpendicular na, to magnetic field. So m v cos theta by qb. Now if you just mug up the formula na, it will become wrong. So that's why I am make you write v perpendicular. Don't mug it like mv sin theta by qb. They can change the angle, again your answer will be wrong. So that's why you write best mv perpendicular by qb for radius. Similarly for pitch, v parallel, you can write for pitch, general formula, v parallel multiplied by time. So in this question, can you tell me what will the pitch full formula in this question? Tell me.
V sin theta into 2 pi m upon q.
See, I am writing. If I write pitch, so distance equals to speed multiplied by time. Speed is what? V sin theta multiplied by time. Time 2 pi m by qb. Correct? Now it is clear, na? Okay, see. Next topic. Force on a current carrying wire in magnetic field. So if a wire, there is current. Current means what? Positive charge is moving. You can think like that. It is the same now, whatever we have studied till now. That charge is moving. So any charge which is moving in magnetic field will experience force. If there is a current in the wire, means some charge is moving. And this wire is placed in the influence of magnetic field. So this will experience force now. Suppose this is the wire and current is flowing, means charge is flowing, charge is having some velocity. And if I keep this wire in magnetic field, so it will experience force, because charge was experiencing force. Same thing here, charge is flowing only, current means what? Moving charge. So charge is moving, and if a moving charge is kept in a magnetic field, it will experience force. Always remember, if a charge is at rest in the magnetic field, what will be the force? Can you tell? If the charge is not moving, the charge is at rest.
Sin 0 0 0.
Sin 0 0 नहीं, velocity 0 ना,
Velocity 0.
थीटा थोड़ी जो वो 0 करना है.
0.
Charge is at rest means velocity is what? 0. Formula is QV cross B. So V is 0 means force 0. And you think now like this. Suppose this is the wire. Current is not flowing. Means charge is at rest. If current is not flowing, means this is normal wire. No current is there. So normal wire, no magnetic field. No normal wire, no magnetic field. I told in the first class. If current is in the wire, then only magnetic field. So normal wire, no magnetic field. So this wire, current is not flowing, means no magnetic field. Now it is kept in a magnetic field. Nothing will happen. Correct? Nothing will happen. Here, if magnetic field is there, suppose current is flowing. Now if current is flowing, what will happen? Magnetic field will be there. And if I take another magnet, so magnetic field will be there. Two magnetic field will interact. So either it will repel or it will attract. Correct? So that's why force on a current carrying wire. So current carrying wire means charge is moving first of all. Same thing. So it will experience force. How much force it experience? You write, like suppose there is magnetic field like this. Okay. And there is a wire. Suppose this is the wire. Length of the wire is L. Suppose length of the wire is L. I current is flowing in the wire in this direction. So it will experience force. How much? You write. Force experienced by this wire will be IL cross B. IL cross B. And again we see the direction of force by the same palm rule. Direction of force, that in which direction force will act. This will be given by palm rule. So first of all, what will the force acting on this wire? IL cross B. Direction of force, palm rule, same. This, our four fingers should point in the direction of magnetic field, same. Our thumb should point in the direction of moving charge or current, in the direction of moving charge or current, and our palm will face in the direction of force. Like here, I can show you magnetic field in this direction. So can I make like this? See, magnetic field in this direction, current is moving in the upward direction. So my palm is facing in this direction, west direction. Can you see? So this will be the force acting on this wire. So in this case, force acting will be in this direction. How much value? IL cross B. Okay. We can write like this also. IL cross B, IL be sin theta or BIL sin theta. Bill. We have the electricity bill. So you can remember like this. Bill. Bill sin theta. Where theta you can say angle between magnetic field and current length vector, where current is there. In this example, see, current and magnetic field are making 90 degree. So this will be sin 90. So directly we can write bill. Okay. So if theta is 90 degree, directly we can write force equals to bill. This theta is what? Angle between, you can write angle between same IL vector and magnetic field. So I am taking the example. You have to tell in which direction force will act, correct? Like suppose my wire is like this and current is flowing in this direction. Magnetic field is like this. In which direction force will act? Right hand palm rule. There.
Northwest.
So see, this is the magnetic field. My 4 fingers should point in the direction of magnetic field. So this is the magnetic field and this is the direction of current. See, this direction. So this will be like this now. So here, this will be the direction of force. So direction of force now you can easily determine na, where will be the direction of force. This is the direction of current. So write it down, this point also.